Of all these civilizations of ancient times, by far the most developed and the most innovative was that of ancient Greece. The era of classical Greek culture, which spread round the Mediterranean basin from about 750 BC onwards, gave rise to a wealth of philosophical and scientific creativity. One classical Greek work, which has been studied for over 2,000 years, was compiled by the mathematician and teacher Euclid of Alexandria, somewhere around 300 BC. The content of this work, the Elements, represents some 3 centuries of Greek mathematical endeavor. Its importance can be appreciated by the fact that since the invention of printing in the 15th century, it's been one of the most reprinted books of all time. Indeed, it may be second only to the Bible in the number of editions that have appeared. Here's the first printed edition, published in Venice in 1482. It's in Latin, and it's the first significant mathematical text to be printed in the West. Here's the first English edition. It's published in 1570. But just why has it been such an admired and studied text for over 2,000 years? To understand this, we must look more closely at its contents. The whole work consists of 13 books, as we call them. The first 4 deal with elementary geometry, the sort of material that's been taught in our schools until recently. But within these books, we can find evidence of different styles, suggesting that a number of traditions have contributed to the elements. Let's now look at Book 1 in detail. Perhaps the most compelling thing we notice is its system of logical proof, a model of what an axiomatic logical structure should look like. Euclid's work begins with a series of 23 definitions. However, because we must have some intuitive basis on which to build, the first few of these are rather vague. The definition of a point as that which has no part means that it can't be split up into any smaller unit. Having got over the basic ideas of point, line, and surface, Euclid is able to define other concepts rather more geometrically. So, for example, a circle is the figure such that all the straight lines falling on it from one specified point are of equal length. Following the definitions, we have 5 postulates. These are geometrical and relate to properties of points, lines, circles, and right angles. The first 3 ensure that the geometrical constructions are restricted to those which can be carried out by straight edge and compass only. The 5th postulate is not as simple as the other 4, and it's been the cause of much controversy over the centuries. It means that if we have a straight line which crosses 2 other straight lines, and if the sum of these 2 angles is less than 2 right angles, then these 2 lines, if produced far enough, will eventually meet. After the postulates, we have 5 common notions, what Aristotle called self-evident truths, like the whole is greater than the part. Then we have a whole series of propositions derived by logical argument from this basis. Here, for instance, the first proposition shows how to construct an equilateral triangle. But merely indicating the construction wasn't good enough. It all had to be rigorously proved that the result of the construction was indeed an equilateral triangle. Here's how it's done. For the given straight line AB, using postulate 3, we draw the circle, center A, radius AB. Then we draw the circle, center B, radius BA. Now, postulate 1 allows us to join these points up. Then we have to prove that this triangle is equilateral. By the definition of a circle, these lengths are both radii of the first circle, so are equal. For the other circle, these lengths are both radii, and so equal. Then, using the first common notion, if these two are equal, and these two are equal, then all three must be equal. The notion of proof wasn't new with Euclid, but it was a product of the Greek classical culture. But how can we be sure that the notion of logical proof began with the Greeks? Well, although there are no surviving mathematical documents from this period of Greek culture, we do have primary sources from other ancient cultures, such as the Babylonian, which goes back to beyond 3000 BC. The Babylonians wrote on clay tablets, which they then baked in the sun, and many of these have come down to us. Here's an example in the British Museum. It shows a number of mathematical problems worked out, including one about a circular wall. And here are astronomical tables. When you see the size of these tablets, one can imagine what wonderful eyesight the scribes must have had. Another ancient civilization was that of Egypt. The Egyptians wrote on stone first and then on papyrus. And examples of both of these have come down to us. Here, for example, is the Rind or Armies papyrus, written in hieratic. It dates from about 1600 or so BC. Here we have a problem solved, and afterwards there are lots of other mathematical calculations. But in none of these Egyptian and Babylonian sources do we have any example of logical proof in the Greek sense, though answers to individual problems are verified. The Greek mathematician credited as the first to carry out a proof was the semi-legendary figure Thales, who is supposed to have lived around 600 BC. It is said that he travelled to Babylonia and Egypt, and from there introduced the study of geometry into Greece. One result attributed to him by the late Greek commentator Proclus is a proof that the diameter of a circle bisects the circle into two equal parts. But we're not told how Thales proved this, and we don't know if his proof would have been acceptable by rigorous Euclidean standards. Euclid's no help either. In the Elements, written some 300 years after Thales, he does not give a proof. Instead, he includes the property as part of his definition of a diameter, writing, "Such a straight line also bisects the circle." Looking at the rest of Book 1, we see it's primarily concerned with properties of lines and angles, of triangles and polygons, and eventually with the result that we know as Pythagoras' theorem, that in a right-angled triangle, the square on the hypotenuse is equal to the sum of the squares on the other two sides, and also its converse. Pythagoras lived about 550 BC, and may have been a pupil of Thales. Like Thales, it's said that he travelled to Babylonia and Egypt. He comes over as a slightly less misty figure than Thales, since there are many references to him. However, most of the stories about him and his followers may be apocryphal. Even Pythagoras' theorem shouldn't be attributed to him. It was known much earlier to both Babylonian and Egyptian calculators. Here's how Euclid proves that the square on the hypotenuse is equal to the sum of the squares on the other two sides. The proof is carried out by equating areas. By dropping this perpendicular, Euclid can show that the area of this triangle is equal to the area of this one. And so the area of this square is equal to the area of this rectangle. Similarly, the area of this square is shown to be equal to the area of this rectangle. And so the result follows. The other three books of this group continue this geometrical theme. Book 2 is concerned with measurement and with equating areas. Book 3 deals with the geometry of the circle. And Book 4 with inscribing and circumscribing polygons in and around circles. Now, the next group of books I shall take out of order. In fact, we don't know what was the original order of the books in Euclid's manuscript. But that's a point I'll come back to later. So let's take books 7 to 9 next. These books are largely arithmetical and are thought to be in the tradition of the Pythagoreans. Book 7 begins with a new set of definitions. We're now entirely concerned with what the Greeks called arithmos, the arithmetic of the positive integers, part of what we today call number theory. One of the propositions compares the ratios of whole numbers. If we have 4 numbers, these say, and if the ratio of the first to the second is the same as the ratio of the third to the fourth, then, by the proposition, the ratio of the first to the third is the same as the ratio of the second to the fourth. Books 8 and 9 continue with arithmos. Book 8 investigates rational roots, whilst Book 9 deals with odd and even numbers, primes, and so on. But now let's get back to books 5 and 6. The origin of these books is much later than that of Book 7. Most of it is attributed to Eudoxus of Cnidus. Eudoxus flourished some 50 years before Euclid compiled the Elements. He was a doctor, philosopher, and astronomer who studied at Plato's Academy in Athens. Book 5 parallels much of what we found in Book 7. Only instead of being confined to whole numbers, it deals with ratios of magnitudes, that is, of lengths and of areas. And many of the results in Book 7 appear here also, but in a different guise. For example, suppose we have these 4 magnitudes to compare. They must all be of the same kind, though, in this case, all lengths. Well, the proposition says that if AB is to AC as DE is to DF, then AB is to DE as AC is to DF. In Book 6, these ideas are extended to areas of geometrical figures. Now we come to the last 4 books. Book 10 is related to Book 13, the last book. So let's look at books 11 and 12 next. Book 11 deals with solid 3-dimensional geometry, and it starts with 28 new definitions. For example, here's the definition of a pyramid as a solid figure contained by planes. And here Euclid makes comparisons between the volumes of different shaped figures with straight edges. Book 12 extends this to the comparison of areas and volumes of curved figures, such as circles, cones, and cylinders. Proposition 2 in this book is attributed to an earlier mathematician, Hippocrates of Chios. Hippocrates lived about 450 BC, and is said to have been the first mathematician to have written a work in the style of the Elements. What Hippocrates said concerns the ratio of areas of two circles. He stated that the ratio of the areas of these circles equals the ratio of the areas of the squares on their diameters. The proof in the Elements, however, is not due to Hippocrates, but to Eudoxus, and uses the method of reductio ad absurdum. It has the following form. We assume first that one ratio is less than the other, and then show that this leads to a contradiction. Then we assume the inequality the other way round, and show this leads to a contradiction also. Having thus exhausted these two possibilities, there's only one conclusion left. The ratios must be equal. Now let's turn to the details of the proof. What sort of contradiction does this first inequality lead to? For convenience, we'll call the ratio of the areas of the squares k. So first, we're assuming the ratio of the areas of the circles is less than k. This is equivalent to saying that the ratio of the area of the large circle to the area of some polygon inscribed in the small circle is equal to k. Now we put to use the ability to construct regular polygons inscribed in circles. We construct a square inside this circle, and then add isosceles triangles on each side so as to construct a regular octagon. Successively doubling the number of sides means that we can construct a regular polygon whose area is as close to the area of the circle as we please. In particular, we can construct a regular polygon in this circle whose area is greater than our first polygon. Now, in Proposition 1 of Book 12, it's been proved that the ratio of areas of similar polygons inscribed in two circles is equal to the ratio of the areas of the squares on their diameters. So we now construct in this larger circle a regular polygon similar to that in the small circle. By Proposition 1, the ratio of these two regular polygons must be k. So we now have two ratios both equal to k. But the area A is greater than the area B. Yet the area C is less than the area D. And this is clearly impossible. So our original assumption must be wrong. The ratio of the areas of the circles cannot be less than the ratio of the areas of the squares on their diameters. A similar argument, first inscribing a polygon in the larger circle, shows that the ratio of the areas of the circles cannot be greater than the ratio of the squares either. Having exhausted these two possibilities, we're left with the only possible conclusion. The ratios must be equal. This remarkable type of proof enabled Eudoxus to prove similar theorems on the relationships of plane and solid figures with curved boundaries in the rest of Book 12. So we're left just with Books 10 and 13. These are thought to include the work of Theaetetus, a young friend of Plato's. We know about him from Plato's dialogue of that name. Book 10 is a long and often difficult work. It deals with commensurable and incommensurable magnitudes, and it provides the groundwork for Book 13, in which Euclid introduces constructions for the so-called 5 Platonic solids. But having said all this, no original manuscript of the Elements has come down to us, or even a reliable copy of the original. No mathematical documents from this period of Greek culture survive. All that we have are copies made centuries later, with changes introduced into them by the editors. In fact, we don't even know if the order of the books of the Elements is Euclid's or that of a later editor. Let's look at some of the printed editions that appeared from the 15th century onwards and that are here in the Turner collection in Kiel University. Here again is the first printed edition, the 1482 edition. and it's based on a manuscript by the 13th century cleric Campanus. Here's another edition, this time from 1505, in which Campanus' work is castigated, saying, "Several wrong and absurd things proposed by Campanus have been arranged, divided up, and corrected." And next, here's the 1509 edition by the Italian friar Luca Pacioli, in which Campanus is completely vindicated. He calls him the most faithful interpreter. And now we come back to the first English edition, the one by Henry Billingsley. It's got copious notes by the editor showing which parts are by Campanus and others. And when we turn over to the end of the book, we get a surprise, because instead of 13 books, there are 16, though the editor does indicate that the last 3 are by other authors than Euclid. And here's a rather nice edition. It's 19th century edition, 1847, by Byrne, and it's full of the most beautiful pictures. And in fact, some of the text itself is replaced by these coloured diagrams. But coming more up to date, here's what we regard as an authoritative English translation. It's in 3 volumes, and it's the one we've been using in the programme. It's by Thomas Heath, and it dates from 1908, and it begins with a long introduction. It's based on a Greek text which was reconstructed in the 19th century. But how did historians go about reconstructing a text which had been lost for centuries and existed only in late amended forms?
Well, what were required were the earliest and most complete editions available. All but one of the 9th or 10th century editions derive from a text of Theon of Alexandria, made in the 4th century AD. But Theon admits that he introduced changes and additions to the text. So these alterations have to be identified. This is just what the French classicist François Peyrat was able to do in part at the beginning of the 19th century, when he discovered a 10th century manuscript originating from the Vatican Library, which he deduced was independent of Theon's text. In the late 19th century, the Danish classicist Johann Ludwig Heiberg took up this, using Peyrat's manuscript and a number of others.
By careful comparison of the sources and by considering the reasons for the differences between them, Heiberg was able to produce what we now regard as the authoritative Greek text of Euclid's Elements.
The Elements is a remarkable compendium of Greek mathematics, stretching from the semi-legendary Thales for a period of some 3 centuries. In it we encounter early Greek number theory, as well as the remarkable work of Eudoxus using proof by exhaustion, and also the work of many other mathematicians, amongst whom we've mentioned Pythagoras and his followers, Hippocrates and Theaetetus. The collection and presentation of all this varied mathematical knowledge in a coherent logical form is one of the great intellectual and educational triumphs of ancient times.